Welcome to everyone. So previous class we were discussing on harmonic oscillations, and we have also drawn that energy levels, and we also discussed the differences between rotational spectrums, how that energy levels here that continuously whenever J is increasing, it means whenever you are going to high energy, that energy difference which increases continuously, whereas for the harmonic oscillations that energy levels remain constant. So now that oscillations, we have that harmonic and anharmonic oscillation. So this is harmonic oscillations. So we have one is harmonic oscillations. Harmonic oscillations. Another one is anharmonic oscillation. And harmonic oscillations. So in harmonic oscillations, we have discussed that how that let me discuss today also. Harmonic oscillations, we have discussed that E is to do by using that B plus half omega naught, and this is in centimeter inverse. The harmonic oscillations, we used to derive that energy. We have to describe this energy levels by using these equations. These energy levels we used to describe by using these equations. And we also discussed that where B is vibrational quantum number, vibrational quantum number, B is vibrational quantum number, and this omega naught, this is actually new, and this is actually, you can say this is wave number, okay, and this is expressed in centimeter inverse, and this omega naught, so we know that B means this wave number equal to 1 upon lambda. So similarly omega naught is also 1 upon lambda, and this and omega this frequency we know that is 1 upon 2 pi k reduced mass. Okay, so if we discuss about this wave number, then we have divided by c. Okay, these things we already discussed, and by using these equations we draw that energy levels. Okay, so now we'll discuss about of that anharmonic oscillations. So see, in harmonic oscillations, whenever you're discussing about of that harmonic oscillations, what you see that harmonic oscillations, what you see that continuously, let's say arrange it this one, and this is continuously like this, means that this graph here continuously getting that equal energy levels. And whereas for anharmonic oscillations, what you see that the difference between anharmonic and harmonic. So anharmonic oscillations somehow says about of that reality, like we see that whenever you stretch any rubber bands, that says A and B, and if you stretch it more and more, let's say after that it will, this bond length will become weak, because whenever you stretch more and more, the bond strength become weak, and after some times it will break it out. So that's what is we saw in harmonic and harmonic oscillations. In harmonic oscillations, we are taking as ideal case that as much as if you stretch it, that it is not breaking. But actually reality, what if whenever you stretch in such a amount that it cannot able to stretch after certain point, then it will break. So that is explained in anharmonic oscillations. So see that after stretching a lot and lot, what happened that it will start to break. Means it should go like this if we look at harmonic, but it will actually really it will break. Okay, so that's what is said in anharmonic oscillations. So here how this equations will say that, so for harmonic what we see, harmonic oscillations, what are the energy levels, how we were explaining that b plus half omega naught, this is in centimeter inverse, sorry, in harmonic oscillations how we are explaining this. Let's say this is energy levels, then we are explaining by taking like this, and this is the energy levels, they have equal distance, and let's say this is b equal to 0, let's say b equal to 1, let's say this is b equal to 2, this is 3, let's say this is b equal to 4. So how we are explaining this energy levels, we are saying by E equal to b plus half omega naught. Okay, and whenever we are discussing about of anharmonic oscillations, that is anharmonic oscillations, how you describe it, that these energy levels like this, after that what it will be, break it out. So instead of going like this for harmonic, it will break it out. Okay, so here also you are explaining the energy level same way, this like this. How these energy levels are coming, I will discuss by the equation. So this for anharmonic, the equations is the same thing, energy E is equal to b plus half omega naught omega, after that just minus, and b plus half square omega xe will come. This is the energy, this energy levels by in this anharmonic oscillations. So here this xe is the anharmonic constant, anharmonic constant. So everything will same except that here that only this much value, so this value will comes with that this square with xe. Okay, so let's say it says that if b equal to 0, then what the value will become, epsilon naught, this is actually epsilon naught because we are taking centimeter inverse, so this is equal to how much, half omega naught minus this square, that will become 1 by 4 because b, this is 0 and this is 1, 1 2 4 omega xe will come. Okay, similarly if b equal to 1, then epsilon will become, this become 3 by 2 because 1 by 2, that is become 3 by 2, that will become 3 by 2 omega, and this is just square of it, that is because this is just square of this value, so this will become 9 by 4 omega xe. Similarly if b equal to 2, then the omega naught energy how much, this is 5 by 2 omega, and this is square of it, that is 25 by 4 omega xe. Similarly b equal to 3, then this will become, that is 7 by 2 omega, and this is square of it, that is 49 by 4, 49 upon 4 omega xe. So like the energy levels will come. So if I draw this energy levels here for anharmonic constants, I will draw like this. So this is when b equal to 0, when b equal to 0, this is b equal to 1, and this is b equal to 2. So you see that energy gaps from here, if I calculate the energy gap. Let's say B equal to 0 to B. So delta B means, sorry, delta E. If I calculate delta E, that is energy gap, then I will write here energy gap I want to calculate, that is so energy gap, that is delta E, that is E2 minus E1. Let's say I will calculate, let's say anyone like B1 to B0. So this is E2, this is E1, or I can say this is E0, this is E1, this is E2, this is E3. Okay, this is because this is the 0 point energy. So we can do E2 minus E1, or also you can do E1 minus E0. So anyone or any from higher energy to like E3 minus E2, that is E final minus E initial. So anyone you can do. So let's me do if I do E2 minus E1, so E2 is pi by 2 omega, delta E is pi by 2 omega minus, that is become 20 by pi, or omega xe. So this value minus which this is for I'm doing this one, then E1 will be 3 by 2 omega minus, that will be 9 by 9 upon 4 omega xe. I'm putting here negative. So what the value it will become, delta E is equal to, so this is pi by 2 omega, and let me I will do 3 by 2 omega, and I will do minus 20 by upon 4 omega xe. This minus minus become plus, that is 9 upon 4 omega xe. Okay, so if you subtract it, then what you will get, 5 by 5 upon 2 minus 3 upon 2, that is going to give how much, 5 3, that is 2 upon 2, that is 1 omega, and this value how much you will get, 25 upon 4 and 9 upon 4, that is equal to 16, that is going to give minus 16 upon 4 omega xe. So this value actually give omega, that delta E is how much, this is 4 16 minus 4 omega xe. Okay, so delta E value is this much, and this is for E2 minus E1 I did. Okay, similarly if I do for E1 minus E0, what the value I am getting, E1 minus E0, delta E is, so what the value I will get, so E1 is 3 by 2, 3 upon 2 omega minus 9 upon 4 omega xe, minus, that will be how much I will get, for E0, that is 1 upon 2 omega minus 1 upon 4 omega xe. Okay, so if I do it, then what the value I will get, 3 upon 2 omega minus 1 upon 2 omega minus 9 upon 4 omega xe, that is become 1 plus 1 upon 4 omega xe. So if I subtract it, then 3 upon 2, that is omega, and this becomes how much, minus 8 upon 4, that is become minus 2 omega xe. So here you see that whenever I do that E1 minus E0, means that transition is J0 to J1, or I can say j equal to 0 to j equal to 1. I'm getting this value, and this is for what? J equal to 1 to j equal to 2. I'm getting this value, j equal to 2. So this value, we see that omega from here, whenever I'm going j equal 1 to j equal 2, I'm subtracting omega from omega for omega e xe, and when j equal 0 to j equal to 1, I'm subtracting minus 2 omega xe. So this value which I'm subtracting, that is get increasing. So this is for 0 to 1, and this is for 1 to 2. Let's say for 2 to 3, what we will get? This is for 1 to 2. Let's take for 2 to 3. Okay, j equal to 2 to j equal to 3. What the value I will get? Let's take delta E is E3 minus E1. Okay, so if I do it, then what the value I'm getting? So 3 by 3 means what the value? And this is the value. Okay, that is 7 upon 2 omega minus, that is 49 upon 4 omega xe minus another is, I'm doing 3 to 2. Then what the value I'm getting? For 2, that is 5 by 2. Okay, 5 by 2 omega, this is minus 25 by 4 omega xe. Okay, so if I do it, then what I will get? 7 upon 2 omega, and this is 49 upon 4 omega xe minus 5 upon 2 omega, this is plus 25 by 4 omega xe. Okay, so if I do it, then what the value I'm getting? See, 7 upon 2 omega minus 5 upon 2 omega, and this is minus 49 upon 4 omega xe plus 25 by 4 omega xe. Okay, so if I do it, then what the value get? I'm omega, and this value is 49 minus 25, that is how much? So that 5, that is 4 here, and that is 2 upon 4 omega xe. That is I'm getting omega minus, that is 6 omega xe. It means that, see the values. So whenever I am doing 0 to 1, I am getting the value this much. This omega I am subtracting 2 xe, and whenever I am doing 1 to 2, then I am subtracting 4, and whenever I am going to this is for 3 to 4 j, I am getting subtracting 6. It means that whenever going to the higher energy, G0 to G1, G1 to G2, this value is getting increasing, which I am subtracting, this getting increasing. See, 0 to 1, 2, and 1 to 2, 4, and 3 to 4, 6. So whenever I am going higher value, this negative value is increasing. It means that the energy levels, whenever you are going higher and higher, this level is get decreases, because I am to subtract more number. The subtracting values from omega is getting increases. Here 2, here 4, here 6. Whenever you are going higher energy, increase. It means that this level is getting decreases and decreases. This value like this. So closely value we are getting. So if I draw the pictures nicely, then how can I draw like this? So whenever this value is like this, like that values I'm getting, and let's say this is b equal to 0, then let's say this is b equal to 1, after that what I am getting decreases a little bit. B equal to 2, then what I am getting again decreases here. B equal to 3, then we say I am decreasing. B equal to 4, like that. After that this value is decreases and decreases. Means here whenever this B0, B1, this gap is high, this gap is high, after that gap is decreases. After that this will be so closely packed whenever you go into higher energy levels. After these points, what happened that actually harmonic, what this would go like this. But for anharmonic, here after certain times this bond get break. So here that bond, this is the bond breaking, that is bond dissociations. Bond dissociations. From here bond get dissociated. Okay. So what we see here that from this to this, just that. This is the bond dissociation point. Okay. After that the bond get break. Okay. So we see that what you say, if I summarize, then whenever I am talking about a rotational or rotational spectroscopy, what I am getting, if this it is, then this length, let's say this is b, this is j equal to rotational, j equal to 0, and this is, let's say, j equal to 1, then this is j equal to 2, and this is j equal to 3, this is j equal to 4. So whenever I'm going to higher energy, this distance is get increases. So this is getting increases whenever going to higher and higher. So in higher, whenever j get, means whenever this is the energy, whenever I'm going to higher energy, the distance between the energy gap is increases. So ongoing, I can write ongoing higher energy gap increases. This is for rotational spectroscopy. This is for rotational spectroscopy. And if I go about of that vibrational, that I am discussing two things. One is harmonic, another is anharmonic. So in harmonic, what you see that, let's say this is, so here that energy gaps are equally placed. Okay, this is, let's say this is b equal to 0, this is b equal to 1, this is b equal to 2, this is b equal to 3, this is b equal to 4, that equally placed. These are the, so here energy gap are equally spaced. And whenever you are discussing about of that anharmonic oscillations, and that time what we see here, sorry, like that, and here that past it is high, Whenever going to higher energy, it decreases. So for that anharmonic, what is say that ongoing higher energy, ongoing higher energy gap decreases. Okay, so these are the two we can look up that rotational spectroscopy how energy gaps are, for harmonic how energy gaps, and for anharmonic how the energy gaps looks like. Okay, so now we will discuss more on anharmonic, because anharmonic is actually the realistics, like after you are stretching more the bond will break. So this is what actually really happens. So we'll discuss more about of that anharmonic oscillations. So anharmonic oscillations. So this, if I get the energy, then I will do like this. Okay, so here that energy gaps are like this. That's it. Like that value, and we see that here, let's say this is b equal to 0 and this is b equal to 1, this is b equal to 2, this is b equal to 3, like that. Then whenever this transitions from b0 to b1 itself happen, and what will be the selection rules for anharmonic? So harmonic the selection rate delta b equal to plus minus 1, that we have already discussed in previous class. For anharmonic, that selection rule delta b is equal to plus minus 1, and selection rule is here also plus minus 1. Okay, so now the thing is that what the maximum, like we have discussed for rotational spectroscopy also, maximum populations will be at b equal to 0, and whenever you go for, because this is the low energy level, and whenever you go for higher energy, let's say b equal to 1, then 1% of b, let's say b0 equal to population is, let's say 100% is there, 100 molecules are there. Whenever b equal to 1, we get only 1 molecules. If 100 molecules are the total molecules, whenever we go to b equal to 1, we get only 1 molecule. So, and whenever you go to that another b equal to 2, then we get that 0.01 molecules, means 1% of ground state that available in b1, and 1% of b1 that is exist in b2. So whenever you go to the higher energy, then the populations will be decreases, means 1% of previous one that will be there. Okay, so maximum transitions will happen from b0 equal to b1, although equally probable, every transitions have equally probable. Whenever you give the electromagnetic radiations, so it equally probable, it may every energy levels get these transitions, means this is equally probable for getting electromagnetic radiations, but the transitions will be occur more where the populations is there. So although these electromagnetic radiations go to b equal to 0, go to b equal to 1, go to b equal to 2, so everybody these have the equally probable, but the transitions will be high when it will fall b equal to 0, because here that huge number of molecules are there. Okay, so according to that, we have that we can say that fundamental vibrations. That this is the most intense. Why? Because this is actually b0 to b1, makes maximum population is b equal to 0. So this is most intense. So because more number of populations means most intense. This is the most intense. So how can you say that this transitions? So this will be E b equal to 1 will be equal to 0 to E b equal to 1. So if I talk about that energy gap, delta E, how can you say E b equal to 1 to E b equal to 0? So here if I do that, so energy is for, because energy for anharmosity is b plus half omega minus b plus half square omega xe. So if I talk about a delta E, that is becomes b plus half omega minus, here again I will subtract minus b plus, okay. So now if I put here delta E, so this delta E here I will first put, this is b equal to 1, this is b equal to 0. So here I will put delta E, so b equal to 1 whenever I put, then this will become 3 upon 2 omega, yes, because of the 1 also that is 3 by 2 omega minus, this is become just square of it, that is 9 upon 4 omega xe, and this is becomes what the value, that is half omega, and this is 1 upon 4 omega xe, and this delta E is this value, what we will get, 3 upon 2 omega minus 1 upon 2 omega minus 9 upon 4 omega xe, this becomes plus 1 upon 4 omega xe. So this delta E value is, but the value this become omega, and this if I subtract, then this is become minus 8 upon 4 omega xe. This delta E you calculate, then this will become omega, this will become 2 omega xe. This is the energy gap, or from this is what, that is b equal to 0 to b equal to 1, okay. If you are doing transitions b equal to 0 to b equal to 1, this will be the energy gap. So this is called the fundamental vibrations, okay. So next we will talk that if so the selection rule for B, this is not that, this is plus minus 1 and also plus minus 2 and plus minus 3, these all plus this all can be the selection rule, but this is the actually highly intense, that is called fundamental vibrations. Also that we have also we can do that transitions that we can say that fast Overton, but that is we can do that b equal to 0 to b equal to 2, whenever b equal to 0 to b equal to 1, that is fundamental vibration. Now I am doing, this is delta b equal to plus minus 2, this is also possible because this selection rule is can be plus minus 2 plus minus 3 plus minus 4 like that, so all are can possible, but the intensity is very less, okay. So this is called whenever b equal 0 to b equal to, that is called fast Overtons. So here also if you calculate that, then you can get let's do it. So if I do it, then delta E will be equal to let's say B plus half omega minus B plus B upon half square omega XE. Okay, and here minus, I will do B plus half and put here omega minus plus half square omega XE. I can do like this. So now if I put delta E here, then here what I do first, B equal to 2, because delta E is, that is E2 minus E1. So here I will put 2, so 2 and this 1 upon 2, 2 to 4, that is 5 upon 2. Yes, this is 2 upon 2, this is 2, 1 so 2, this is 2, that is equal to 4, and 4 1 is 5 by 2 upon 5 by 2 omega, and this is square of it, that is 25 upon 4 omega XE. Okay, and for 0, that is half, and this is 1 upon 4 omega XE. So if I do it, then what the value I will get? This is 5 by 2 omega, and I will take here minus by 2 omega, and I will put this one minus 25 by 4 omega XE, and this minus minus become plus 1 upon 4 omega XE. So delta E is, this is equal to how much? 4, that is equal to omega, and this value will become how much? Minus 24, so that is equal to 6 omega XE. Yes, that is 24 minus 6 omega XE. So this one I can write, this value I can write 2, so I can put 2 omega common, then 1 upon 3 omega X. Okay, so this is the energy gap if this is for first Overton. Okay, similarly for second Overton also we can go. So let's calculate for second Overton also. Second Overton, that is B equal to 0 to B equal to 3. Okay, so energy delta E is E, that is B equal to 3 minus E, B equal to 0. This one also you can do easily. Delta E is this will be B plus half omega minus B plus half square omega XE. I can write, and minus, that is B plus half minus B plus half square omega A. Okay, so here if I put delta E, then this is actually 3, I put 3, so this is 3, then that is 6, that is because 7 upon 2, just because 3, and because this is 3 by 1, 3 upon 1, so multiply by 2, that's equal to 6 upon 2, 6 upon 2 plus 1 by 2, that's 7 upon 2, I will write 7 upon 2 omega minus this, I can write this square it, that is 49 upon 4 omega XE, and minus this is 1 upon 2 omega, and this is 1 upon 4 here, this omega XE. So here if I put this value delta E, this is become how much? 7 upon 2 omega minus 1 upon 2 omega, and here I will put 49 upon 4 omega XE. This minus minus become plus, So 1 upon 4 omega xe. So here also if you calculate it, then what will the value? 7 upon 2 minus 1 upon 2, that is 6, that is equal to 3. Okay, 6. So that is 6, 3, and this value, how much you will get? 49 minus 1, 48, and 6, that is equal to 12. 12 for the 48, that is equal to 12 omega xe. Okay, so now this delta E value will be, if I put that 3 omega, if I common it, then this 1, this become 4 omega xe. So this is for the third order terms. Okay, so this is for third order term. So guys, if you notice it, for this is for second order terms, and this is for first order terms. So this is for fundamental, I think b equal to 0. This is for fundamental vibrations, and this is for first order terms. For first order terms, first order term, because this is for b0 to b1. Okay, b0 to b2, that is first order term. This is for second order terms. So if we look it, then here we see that 2 omega 1 minus 3 omega e xe, and whenever I am going to this 3 omega 1 minus 4 xe, means here we see that 2, here it gets 3, and here it was 1 3, it become 1 4. So what we see that if you go for third Overton, what you see that here 3, previously that was 2, so it become now 4 omega, and this is 1, and this become 5. This is for third Overton. Similarly, if you calculate, we can get it that these things. And if you go for delta E or fourth Overton, what you say, this 4, it will become 5, and this is 1, and this 5 become the 6. I can write 1 minus 6 xe. This is for fourth, and if I get again, then what I say, 6 1 minus 7 omega xe, like this. This value is simply that this value is increases by 1, and this value is increases by 1, like that we can go for fifth order terms, like that. Okay, so these are the when transition is b0 to b2 or b3 b4, but the transition is started from b0, and that may be b3, maybe b4, all that. So these are all called that first overtone, second overtone, third overtones, and that fundamental vibrations. Okay, now the question is that whenever this is the transitions, let's say, so this is the energy, so if this is that, like this, so whenever I say that here, see that this is decreases like that. So what we see that whenever I'm doing the transition, this is equal to b equal to 0, b equal to 1, this is b equal to 2, this is b equal to 3. Whenever I'm doing transitions from here to here, because here is higher populations, but if I do heated it, if I heat it, this one, if I provide the heat, then what happened, that number of populations from b0 to b1 will go, and now the populations will be high here. So now if you give this radiations, then the transitions here also will give the good intensity. So it means that B equal to 1 to B equal to 2 transitions. If you heat it, whenever you give no heat, then the very less intensity will get. But after giving heat, that number of molecules which were B equal to 0 is there, that are shifted to this energy. Now here, after heating, here the population is high. Now if we give electromagnetic radiation, now here also transition is occur everywhere, but after heating, intensity here also we get good amount as like here. So on that case, we are saying that hot bed. Hot bed means after heating. Okay. So for that, if we calculate that delta E, then I will calculate E B equal to 2 minus E B equal to 1. Okay. So now if we calculate that, then I will calculate delta E. So I can calculate by saying minus B plus half square omega XE minus plus half minus B plus half square omega XE. Okay. So now this B equal to 2, so I will put here this is the hot band, so B equal to 2, that is 2 means 1, that is become 3 by 2 omega minus this is become 9 upon 4 omega x, and this is 1, so 1 upon 1 is, so this is become sorry so this is delta E. So whenever this become 2, then that become 4, that become 5 by 5 upon 2 omega, this is 20 by 25 upon 4 omega XE, and this is, now this is 1, so this is become 3 upon 2 omega minus that is become 9 upon 4 omega XE. Okay, so if I remove it, then this is 5 upon 2 omega, and I can put here minus 3 upon 2 omega, and now minus 25 upon 4 omega XE. This is minus get plus, that is 9 upon 4 omega XE. So here delta E is going to be 5 upon 2, that is 2, that is equal to omega. Okay, omega, and this is minus 25 upon 9, that is become 20, that is 16, become minus 4, okay, omega XE. So this is the hot band, that is in transitions from B1 to B2. Okay, that is omega 25 minus 4, that is 20. Okay, so this is for hot band. Okay, so these are all about of that anharmonic oscillations. Now that whenever you are talking about of diatomic molecules, or you talk about of that any rigid rotor, or any, if I talk about of what I said that any diatomic molecules, if I talk about of the diatomic molecules, then diatomic molecules, what is there here? Both diatomic molecule, this is the linear molecules, so here both rotational and vibrational will comes, vibrational. So if I talk about of it, then how can I tell, just a minute. So before dynamic molecules, I should start vibrating rotors. Okay. Sorry for confusion. Vibrating rotor. So vibrating rotor, what we say that total energy equal to vibrational energy plus E vibrational plus E rotational. Okay. So this E vibrational, or I can write E rotational plus E vibrational. So E rotational means we know that B, J and J plus 1, and that is also with minus Bj square and J plus 1 square. Okay. This plus after that vibrational, that is B plus R minus B plus half square omega xe and minus again yes, this amount we have to do. This the total means this is for rotational and this is for vibrational. So vibrational means we will talk about of that anharmonic oscillations. Okay, so now what is here, that since D is very less, means B is compared to B, D is very less. So what we do that we neglect maximum times D because it is very less compared to B. So now the total energy means maximum times, because this value is very less, but if it is comparable then we can consider it, but maximum time it is very less, so we neglect it. So we will write simply Bj J plus 1 plus B plus half minus B plus half square omega xe. Okay, so this is the actually the vibrating rotors, the total energy. So now we will discuss about of the diatomic molecules, or we will discuss diatomic molecules in next class. So today up to this, thank you.